Hello, my name is Jess Thayer, and I'm working on a predictive forward dynamic simulation of human gait. Though learning to walk is a natural part of human development, current understanding of human gait is limited, inhibiting the application and development of gait-related treatments and medical devices, such as prosthetics and orthotics. A better understanding of human gait, both normal and pathological, is necessary to improve the development and fitting of prosthetics and orthotics for amputees. Improvement of these devices requires gait models that allow for the prediction of normal and pathological gait so that experimental gait analyses are not required of the patient. Using an existing gait model and control system proposed by Soon, this research improves the performance criteria used within the optimization framework to better model gait generation by the central nervous system. The three aims of this thesis are to expand the Soon model to predict a subject-specific gait cycle, develop cost functions consistent with existing literature to better mimic central nervous system control of the body, and to evaluate controller performance using clinical gait analysis measures in prediction of both normal and abnormal human gait. The Soon model proposes a model predictive control framework, which is a good approach for the control of a human gait model because of its predictive formulation. The simple MPC schematic shown here demonstrates the predictive aspect of the MPC control scheme. Given some target gait descriptors such as step length or center of mass velocity, the control input to the gait dynamics model is optimized according to the error between the target kinematic reference and the predicted kinematic output of an internal model to the end of the gait cycle. This internal model is a state-space dynamic model, which is a simplification of the full plant. The predicted control output is then applied to the plant for a specific time before the process is repeated. This iterative optimization continues until the end of the simulation period. The work of this project is focused on an improvement of the optimization framework and examines both the cost functions and model constraints. There is significant evidence that minimizing metabolic cost is a primary optimization target in human gait. This work introduces two new optimization criteria: work on the center of mass and dynamic effort, which are used in addition to simulation constraints such as joint range of motion limits and are considered mechanical approximations of metabolic cost. A resulting simulation of 1/2 gait cycle, which was achieved using a center of mass energy cost function, is shown here. Resulting joint trajectories from these simulations can be compared with subject-specific gait data, the Soon model, and a normal ambulator database from the OREC Gait Lab. The simulation framework is currently limited by the complexity of the optimization solution space and must be improved to reliably meet constraints without reducing the predictive capability of the model. However, the new cost functions containing effort-type optimization targets show promise by generating joint trajectories more similar to subject data than the Soon model. Future work will continue to explore what motivates human walking patterns by developing fatigue optimization targets that work with a mechanical model. Thank you.